Once again, talking about correlation, we can start by looking at this graph right over here of a scatter plot. Now, looking at this, there's some sort of maybe moderate, positive, linear association. So negative, that takes this one out of the running. Not linear, that takes that one out of the running. There is no association? No, definitely C. If we standardize both variables, what would the correlation coefficient be between the standardized variables? Now here's the important concept right here. When we measure variables, it doesn't matter what units we put to them. Standardizing them would put them into z-scores, which are unitless measures. But once again, if x and y are correlated, then the correlation remains the same no matter what we use to describe them. Height in inches is the same as relating it to height in feet to something else. If we had measured median family income in thousands of dollars instead of dollars, how would this change the correlation? Once again, the same concept right here. It's not going to change it at all. We can't really change correlation by changing the way we measure the variable. It'd be like tricking statistics. It's all of a sudden, wait, height and weight are not correlated now because we changed it to pounds instead of kilograms. Now the relationship has changed. You'll get lighter as you get taller. It's not like that. Another state has a housing cost index of 230. So housing cost index 230 would be down here somewhere, and a median income of 58 over here. Now if you look, that's going to hurt the relationship. Kind of brings out the ellipse. So something down here, 230 and 58, is going to harm the relationship. Correlation would be lower. Does the data provide proof? Proof, right there. Right there, that's all we need to read. Correlation never proves causation. Big concept right there. We can never prove it no matter how high R or R squared is in the next chapter. We can never prove one variable causes another. Even with an R squared of 1 or an R of 1, we can't prove it. Going on to the next question here, we have some data. Find the correlation between these data. Now do not work this by hand. Whatever you do not work this by hand. Be a big mistake. Go to Make Tab Delimited Copy. We can click on this right here, and we'll go over to Jump. Now with Jump open, you can go to File and New Data Table. I already have one open. Now before clicking anything, we do not click on the data table. I can't make that clear enough. We need to go to Paste with Column Names. And you'll notice you have your data in here. Now on Macs, it does kind of put spaces between. That won't mess it up. Jump will actually skip over those rows right there. We need to go to Analyze, Multivariate Method, Multivariate. We need to find the correlation between time and calories. Now they should be blue. If you do not have blue right here, you've made a mistake, and you might have inserted it and removed it. Open up a new data table and then put the data in fresh, but don't click on it. So very important right there. So now we see the correlation is negative, meaning the longer someone spends at the table, the less they eat. This is a topic talking about children apparently. So apparently children who just don't want to eat spend longer at the table and they consume less calories. And so the correlation is negative 6.6193. So negative 0.619. If time were recorded in hours, how would this change it? It's not going to change it at all. Correlation is unaffected by scale, so it would not change. Same concept as before. Explain what this correlation means for these data. What it means is exactly what we said before. There is definitely a negative correlation, and 0.6 is more moderate than weak. Weak is about 0.3, moderate is about 0.6, strong is about 0.9. Those are all just general guidelines. Perfect would be 1 or negative 1, and non-existent or no linear correlation would be 0. Once again, correlation only has values between negative 1, perfect negative, and positive 1, perfect positive. And we can see tolerants who spend more time at the table consumed fewer calories, as we stated before. Evidently, something about being at the table causes them to lose their appetites. What is the conclusion? Well, we have the conclusion would be speculative, because when we talk about this, we can't exactly know that for certain. The statistics show this, but we don't know something is causing them to lose their appetite. The word cause there is really, really bad. We don't want to talk about cause or prove. Those are things we can't do with statistics. We can only show evidence or stronger evidence. That's all we can do with statistics. Sorry. Going on to the next problem right here. We have fat measured in calories and fat measured in grams, and sodium measured in milligrams. How are the fat and sodium contents associated? Well, let's make a tab delimited copy of this and go back over to jump. And we're going to open up a new data table with Command New or Control N. You can also do it right up here, and you will also see the shortcut for a new data table on a Mac. It is Command N. So we have the new data table open, and we need to paste with column names again because it has column names, and we see the same thing right here. And we can go ahead and graph the relationship in a scatter plot. Multivariate methods, multivariate under Analyze. Click both of them. They should both be blue. And here we are. Well, there is a positive correlation between fat and sodium, but it's really, really, really weak. And if you notice, if you were to remove, let's say, this point up here and rerun it, my guess is the relationship would go away. This is very weak. So 0.1051 is a very weak positive association. It doesn't really have a curve to it, so we need the word positive. Well, let's see here. Strong, weak. I wouldn't go with curved. I'm going to go with there's no association because it's so weak. Yours should be similar. When we get down to about 0.1, 0.2 correlation, especially with 5 points, it's not really significant. And let's look at that for a moment. Right here, we have the relationship, and we can find out if it is significant. This is a very important thing for the test. So let's open this up a little bit more. The question is, well, there's correlation here, yes, but is it significant? That would be a factor of the p-value. The p-value denotes significance. I went to pairwise correlations to find the significance between all of our pairs. And if you notice, the correlation 0 is really contained in this interval. It's telling us it could be really negative or it could be really positive. We'll talk more about confidence intervals later. But since 0 is contained in there, we're saying it's possible there could be 0 correlation. And the p-value right here is saying that this would happen by chance 86% of the time. So yeah, I think it happened by chance. 86% of the time it could happen by chance. So yeah, it definitely happened by chance. This is not some real relationship. So with that in mind, let's go on to the next part of this. That's it. I do think there is something to this problem. Look over the p-values and find that for this problem. Just try to understand the deeper concepts that this wants. A lot of people just skip over this problem and maybe guess through it, especially if they already know the answer. I do see a slight bend in this just looking at this. QQ, quantitative, quantitative, straight enough, maybe a problem. Outliers, maybe a problem. Remember, QQ is the only black and white one that, yes, we meet the conditions. So let's see here. Does the scatter plot indicate that it's appropriate to calculate a correlation? Let's see. No, because there are too many outliers. Let's see here. It wouldn't definitely be no because there's not quantitative variables because they're both quantitative. We're going to go with yes. And it's not because it's positive. It could be negative. It appears to be straight enough. That's straight enough. Yeah, it's got a little bend, but straight enough. Are the outliers really big and bad? No. Once again, straight enough does not mean positive. Some people think it's straight and up. No, no, no. It's straight enough. Does the association between attendance and run score describe it? Well, it's definitely positive. That eliminates it. And it's definitely at least strong or moderate. You would not go with weak. If you're trying to figure out how to, some people might ask, well, we do have the correlation here, but without looking at that, you can draw your ellipse around it. The more it looks like a 1 or the more it looks like a 0, if all the points were scattered out in the 0 pattern, then it would be closer to 0 correlation. And once again, remember, we can have a relationship without it being linear correlation. We could have something that bends, and then we would say it has correlation, just not linear. or relationship. Does this prove? Right there. No. There is no evidence. Wouldn't be there's no basis. Let's see here. There's no evidence of an association. No, we do have evidence. Let's make sure we get this right. We do have evidence, but we can't prove it. There's no basis to make the claim of causation. That is this whole homework. Don't be tricked. It really hits up the topics on this homework of correlation does not prove causation, because a lot of times we can have a third factor that comes into play. Also, these weren't experiments. Also, we don't know the directionality of it. Does X cause Y, or does Y cause X? Or as I mentioned, some third variable like Z, as for example are shark attacks and ice cream sales. They're both caused by summertime. So definitely go over this homework. Pretty easy homework, easy one to get 100 on, but try when you use JUMP to bring up the pairwise correlations and look at the p-values. Let's go back and look at the other one we had from the other data set. I think it's right over here. So this is our first one we did with the children sitting at the table. And so my question here now for this one would be, is this significant correlation? This is the children sitting at the table. And we can go here to pairwise correlations. I'm guessing, oh, it's not significant. And you'll see that a lot of times. There's not that many data points. Correlation would have to be very strong for it to be significant. So we actually don't have significant correlation here denoted by this p-value. The lower the p-value, the more significant it is. Very good concept for the test. Low p-values, more significant. Good luck with this assignment.